All right, good afternoon, and thank you for visiting my talk. My name is Andrew Patt, and I'm a bioinformatics scientist at the National Center for Advancing Translational Sciences. Today I'm going to talk about better approaches for functional interpretation of metabolite data. This is my first time speaking at GLBIO, and I know not everyone in the bioinformatics community is intimately familiar with the nuances of metabolomic data analysis. I was browsing Reddit the other day and noticed this thread on the top of the bioinformatics forum, which I think summarizes the general attitude towards metabolomics data well. In case you can't read it, it says, "I feel like I'm missing something. I work a lot on the integration of omics data, but have so far made zero biological insights by including the metabolomics data." Despite the fact that the thread got high visibility, there was very little offered in the way of actual solutions. Fortunately, that's what I'm here to talk about today. Most people don't need convincing that metabolomics data are useful, as metabolites exhibit a close relationship with phenotype and outcomes. However, properties of the data have hindered the impact of metabolomics in bioinformatics research. This can largely be attributed to a lack of centralization of resources, leading to analysis paralysis. To address these issues, I'm going to talk about two complementary tools that our group have developed, RaMP-DB and MetaboSPAN. RaMP-DB, or the Relational Database of Metabolic Pathways, is an open-source downloadable metadatabase that harmonizes annotations from a variety of open-source databases for functional annotations of both metabolites and genes. RaMP-DB is constantly being developed, and as such is up-to-date, versioned, and contains comprehensive annotations from its source databases. RaMP-DB is designed to be accessible and usable by both computational and non-computational users, either through our online interface or through our R package and API combination. Meanwhile, MetaboSPAN is a metabolomic functional enrichment workflow that addresses gaps in metabolite pathway analysis using annotations that are derived from the RaMP database. As I mentioned on the previous slide, RaMP-DB is constantly undergoing development, and we're currently on the 2.3.1 release of the database. Some notable features of this version are displayed here. A major focus of recent updates has been to include a wider breadth of lipid annotations, including synonyms, chemical structures, and chemical class, which are available for all metabolites in RaMP now. To leverage this new information, we've implemented new modules in the R package and website, including a chemical class enrichment module, the option to specify biospecimen backgrounds for standard pathway analysis, such as liver or heart tissue backgrounds, and a new pathway analysis results plotting tool. Lastly, we're excited for an upcoming release that will include a reactions corpus for RaMP metabolites and genes derived from the RAIA database, opening up new opportunities for data annotation and exploration. Despite RaMP's usefulness in providing comprehensive functional annotations for multi-omic data, there are still some issues with metabolomics data interpretation that we felt weren't addressed by our current pathway analysis methodology. For example, anyone who's worked with mass spec or NMR technologies knows that it's impossible to consistently detect all metabolites in a biospecimen with a single assay, which leads to incomplete and inconsistent metabolite measurements. Even if these features are detected, it's often difficult to correctly identify them due to gaps in spectral databases. Lastly, many metabolites don't have functional annotations associated with them, which is an issue that's partially ameliorated by RaMP-DB. To tackle these issues, we propose a similarity network-based approach. We constructed a variety of metabolite similarity network models that describe functional overlaps between metabolites within RaMP-DB. As one might expect, these networks are highly modular, with tight clusters of functionally related metabolites. In these graphs, nodes represent metabolites, while edges are weighted and encode the shared annotations between adjacent nodes. For example, in our pathway similarity graphs, edges are weighted by an overlap index, which describes shared pathways between two metabolites. Like for pathway analysis in RaMP, we constructed these network models for lists of biospecimens stored in RaMP-DB, as well as for all metabolites within the database. We used these knowledge graphs to increase the scope of pathway analyses in metabolite data in order to reduce the reliance on consistent detection and identification. To do this, we overlaid metabolites of interest onto our knowledge graphs and used network topological properties to extract relevant neighborhoods of metabolites that were highly proximal to the input set. The network topology was described using a Markov random walk with restarts, which allowed us to correct for bias introduced by network connectivity and centrality. We wanted to ensure that MetaboSPAN passed muster under rigorous validation, and so we performed a variety of experiments with simulated or real data that allowed us to measure MetaboSPAN's performance against a variety of state-of-the-art metabolomics pathway analysis methods. These experiments included measurement of false positive rates in randomized data, testing recovery of seeded true positives in simulated data, comparing overlap of findings in different data sets measured on the same samples, and testing robustness to alterations in sample size. Importantly, we had to ensure that the same pathway library was applied across all approaches and experiments to ensure the parity of our results. Come to our poster to see the results of some of these validation experiments. As a quick proof of concept, we applied MetaboSPAN to a real dataset generated by our group in a study comparing the metabolomes of dedifferentiated liposarcoma cell lines, stratified by their MDM2 copy numbers. We compared the results of MetaboSPAN analysis to those of classic Fisher's exact test analysis. We found that MetaboSPAN successfully highlighted several pathways known to be relevant to sarcomas in the literature that were missed by the Fisher's test, including sphingolipid synthesis, pro-inflammatory lipid synthesis, bile acid pathways, and beta oxidation. In conclusion, RaMP-DB is an online interface, an R package, and an API that can be used to functionally annotate your metabolite or transcript data, as well as to perform functional enrichment analyses, both pathway and chemical class level analyses. RaMP-DB is constantly being developed, provides comprehensive annotations for metabolites, and is usable by both computational and non-computational users. Meanwhile, MetaboSPAN is a novel metabolite functional enrichment workflow that addresses some of the limitations of metabolomics technologies by leveraging RaMP-DB annotations in order to fill in blind spots of untargeted metabolite functional enrichment analysis. I'd like to thank our team here at NCATS who have contributed extensively to both of these works, as well as our support team at NCATS and our external collaborators who played advisement roles in both of these projects. I've included here links both to our online website, to our GitHub repo for our source code for RaMP-DB, and as well as my email if you're interested in testing the MetaboSPAN R package, which is not currently publicly available, but hopefully will be soon. And lastly, please check out our poster if you want to learn more about either of these tools. Thank you.